All right, so welcome everyone to our programming languages lecture. Today we will start talking about functional programming, a different approach to programming than usual, the first imperative approach. Again, some of you, actually you'll find out that most of you already use some concepts from this functional programming. But before we start with the actual languages, again, we'll see maybe some background what led to this invention of these type of languages, this approach to computing. And so this will go back again to Alonzo Church and his famous Lambda Calculus, or infamous again, so this goes back to 1930s. Again, I will be using my repository, code spaces. You can use Colab if you want, right? The links are here, right? So I'll open up in a code space so I can add some changes maybe. It should be alive. Let's open it up. All right, so what's good there? Probably not related to programming, right? So, almost. Right, so again, why should we actually care about today's lecture? Of course, is that actually the concepts actually are used in everyday most modern languages include some of this functionality, pun intended. Right. So again, if you don't want to read all or don't want to listen to me today, the main thing is no side effects, no mutability. Right. That's the main tenet of the functional programming. Right. So this idea is kind of pure, that everything is a mathematical function, basically. You don't change data outside. Something comes in, bless you, and something comes out. Again, we can call it declarative paradigm. Basically, we just express things, and we don't really say exactly how things will be done. This is actually, of course, debatable. Maybe it's not really purely declarative, right? And one other thing is, of course, is that functions are first-class citizens, meaning you pass around functions as arguments, right? So pure functions. You have higher order functions, heavy use of recursion, right? So in fact, some languages go as far as don't include loops whatsoever, right? So some do, but then again, it's considered a dirty deal to use loops, actually, right? So we'll see how it works. Again, and one of the core concepts, of course, is something called referential transparency. We'll look into this deeper. But the idea is very simple. Basically, we can replace the value of the function. We can replace the function with its value, basically, for a particular argument. Right? So it goes together with a pure function. Again, we'll talk about lazy evaluation. Strong typing, that's more for the languages. So there's the purest of the functional languages, a language called Haskell. You're open to write report or explore it yourself. I would say it's too pure. It would be good for academic setting, actually, but it's not very practical. There are some people who differ, but Lisp actually is the original, the granddaddy of the functional languages, and we'll be looking at a version of it. It's called Clojure, right? There's also Erlang, F#, Scheme, which is another Lisp variant, OCaml, right? But we'll see things like JavaScript and even Python include many elements and actually let you write programming your code in functional style. So there is some big advantages, especially debugging, testing, also sometimes concurrency is easier to implement. It does have a steeper learning curve, right? So there's another downside to functional programming is that you end up writing your own language usually. You use this language, you end up writing something for yourself, right? You can start with something very simple and you can build your own sort of say building something for yourself, but the problem, of course, building something for yourself is that other people, your group mates, your colleagues, your friends, your enemies, right, they will not be able to understand what you meant. That's a downside, right? So, but let's go to history, right? So Alonzo Church, so he invented this concept of Lambda Calculus. It's a very formal system. Again, he was a logician, mathematician, and his big idea in those days, he's not alone. Idea was to have this sort of formal model for computation, right, around the same time, 1936, I believe it was. Turing, of course, was more famous, more well known. who invented Turing machine, again, before digital computers. But his Turing machine is actually what we use in hardware, on a hardware level. But it was proven, of course, that the Church's approach and Turing's approach were equivalent, right? The Church-Turing thesis, right? So, but then we get to John McCarthy. I forget how was he actually? He's unfortunately, he's dead now. I think died in 2011, I believe. Right? Let's see. But was he actually a student of Alonzo Church, or was he just deeply influenced by him? Let's see his obituary, right? 84 years old, right? He was one of the, again, grandfathers of AI, right? Because Lisp was basically the AI language of the day, right? So heavy influence. Now the question is Church here? Church? No, I don't see it here in official ACM obituary, but yeah, but he definitely was. He read, right, in 1950s, right? We didn't have Python, we didn't have Ruby, we didn't have JavaScript, right? But yeah, so this was basically the earliest functional language. You can still do some imperative things like, you know, loop things, like well, modern versions of support object-oriented programming as well. But again, it's heavily inspired by Lambda Calculus, right? Again, Church mathematical logic, right? But intellectually, they were basically related again. So this is basically what shapes today's modern languages, right? Again, pretty much every language. Let's see, which language doesn't have anything from functional programming? Well, original Java did not have it, right? Original Java, right? Original C++ also no. But first of all, you could always make your own Lisp in C++, right? But nowadays, all languages include Lambda functions, you know, and functions of first-class citizens, things like that, basically, right? Yeah. So pure regular C and regular C does not support this approach, but even C++ has many things now. So the influence has spread, right? So let's talk about this first. This formal Lambda calculus, which led to this, right? Maybe I will. So, idea was this: to have variables, right? About the shocking concept like a variable, right? There's some sort of abstraction, right? And basically, abstraction is to use this lambda, right? What is lambda? Is basically he used the lambda as something not used by for other things at the time, you know, in mathematics, right? So okay. Lambda is not used, I'll take it, you know. I'm sure it is used for something else before, but probably not something very important, right, you know. So pi is used, alpha, omega, gamma, right, but lambda was apparently not very, was not taken, so he used lambda. So it basically, well, this is really rough analogy, it's basically like a function, right. It's like that, and you basically provide, it lets you bind, or how should I say, abstract over some parameter, input variable. In this case, it's x. Maybe I will show you an example on, again, on my friend Paint, right? So he used, let me do Paint. So there are different notations, right? So something like, and in a book here, in official materials, again, the way he originalized, he used dot, right? We can use also parentheses, right? It doesn't really matter, right? So let's look at this example, right? This is really, really stupid example, but still an example, right? So, right, lambda x, right, dot x. So this is all it says. You input. So in Python terms, we would say, you know, it'd be like something define, you know, my function, you know, fun, you know, f, you know, x, right, and return x, right? Return x, right? Except, of course, we don't really have the name for f, right? We don't even have the name. It actually be an anonymous function, but something like that, basically, right? Gives you out x. X comes in, x comes out, right? So you have, so we can call it, right? Of course, right? So you can call this function, right? Basically, you know, x dot x, and we take 5, right? And then out comes 5, right? Really stupid, right? I mean, it means since what's the use? I mean, it's just a, you know, gets you back, but at least you get the idea, right? Sometimes, right? Some other materials write it like this, you know, like x, and use like maybe x, right? Or we can use also, depending on program language, x, maybe you know, x, right? Something like that, you know. Original paper, I think by Lambda, by Church, used dot, right? They didn't use parentheses at the time. It was not a, you know, but the Lisp type of language, you'll see parentheses, right? So same thing, right? Same thing. And then you call it something, right? So, so that's the basic idea. Let's make a new, can we make new, right? All right, something, come on, new, oh yeah. Do you want to save this? No, I don't really want to save it. Do I really want to? No, maybe I'll save Lambda. I'll have to type it something. Right. So really simple concept, right? So we'll go to something a little bit more complex, right? So we could say something like, and again, x, and we'll say maybe, I don't know, all right, so x, and again, x plus, right, again, x plus, say, 3, right? So obviously, right, and if you call it with something like 8, right, and you call it basically, right? So it's going to be, of course, 11, right? I mean, not shocking, right? I mean, so that's the basic idea, right? So what's interesting is, now, how do you get to multi-parameters, right? Most modern functional programming language will let you use multiple parameters, but the original approach, right? His approach actually, and actually it's still allowed in functional programming, right? Is that actually we can have multiple, we can sort of, so basically this variable is bound to this inner part, right? It's not free anymore, right? So what, let's say you have a, let's say you have something like, I don't know, let's say a function would be something like, I don't know, x2 plus y2, right? What does this function do? It's assuming these are coordinates, right? This is Euclidean, right? Distance, right? Yeah, something like this, right? So how would you write this, right? So, okay, you have, okay, so you originally you can't do like, you're not allowed to do this, right? It seems like you would want to do this, right? But I think original approach, you don't do this, right? So 2 parameters, right? Instead I'll do back, right? Undo, right? So his approach is basically like this. You bind 1, let's say you bind x, right, dot, and you bind also y. And of course, in this case, you can see that it doesn't really matter. The order, right, up to you, right? You know, these are just names, right? So obviously, again, this whole approach was, remember, this idea was to have this ground-based, from very, very basic steps to build this model of computation, how you can commute anything, right? So, yeah, and of course now you can supply like, I don't know, you know, I guess, what's the name, 10 and 12 and 5, right? 12 and 5, right? And your back comes out 13, right? Is it correct? Yeah, I think so, right? Right, something like that, right? So, yeah, so that's the basic idea. Of course, again, out of this simple model, right, I don't think actually he even had, I don't know how, he also defined, I think, like in those days, even numbers right, as well, right, the church numericals, right, how you define them from nothing. So, hopefully you get the ideas. So again, you have some, because you could have some data, right, you can have some variables outside of this, right, some data which are not bound to these, right, something like A or B or Z, right. But of course, here the goal is to have everything tightly bound, right? So again, in comes something, out comes something, right? Okay. Now, simple idea, right? Abstraction, right? So application, you apply, you can see in these details, right? Something like this. So this is identity. In comes 5, out comes 5. In 5 plus 1, right? So here you have x, y, x, right? A 2-variable function, the result is 7, right? But of course, why? Because what happened to the 8? Because 8 is not used, actually, right? This actually was identity, right? Kind of silly example here, right? So, variables, abstraction, right? And what makes things maybe, where things get complex is already that E, right, the lambda term, right? It could be anything, right? So, there's a lot of, you can do recursive things, right? So again, but the reduction, of course, this is what we know. Right. So, beta reduction is what we saw, right? You substitute the argument into function and you get the results out. There's also off conversion, rename bound variables. Well, yeah. I mean, obviously, the name of the variable doesn't matter. XA, you know, name, whatever, right? There's also simplifying functions, right? Again, when valid, right? So, again, so it was proven, despite this completely minimalistic syntax, that you can do same thing as in regular Turing machine. So this means by extension, or any machine we use today, right? We can use this type of lambda calculus, and vice versa, right? So we can emulate one or another, basically, right? There's a video by Computer File, I think pretty good, pretty decent video, right? There's also Lambda Calculus, and also the Stanford Encyclopedia of Philosophy is pretty good. Has a pretty good article on this. Let me allow this, right? Of course, there's some philosophical implications, right, for this, right? Yeah, you can see some examples here, I think. Yeah, something like that, yeah. On syntax, right, we saw the syntax, we saw the variables, but again, it gets quite abstract when you start doing things, once do something more complex. Where's my code space? I'm not in my code space. Where's my code space? I'll take this one off. I don't want in this. Where's my code space? Oh, come on. I thought I opened up. Oh, John McCarthy. There we go, right. So, okay. So variables, syntax reduction. Yeah, there's something you might heard of combinators. Y Combinator, of course, one of the more famous ones. But it's basically lambda term with no free variables, right? So identity, of course, is just a name, right? So I, right, meaning you define this, you know, what I wrote on our paint, right? That it basically returns the input, right? That's one simple combinator, right? You know, constant combinator. Let's take a look at this one here. Right, so it takes two arguments, right, but it always turns it ignores the second one, right, input 510, because it will return the first one, right. Sometimes use fixed values. Apply or call a combinator, right. So you have two functions, x and y functions, right, and you apply them to the same argument. So notice here, right, that these are actually function calls, right. X and y basically are functions in this case, right? So you define lambda x is x plus 1, lambda 2 is x plus 2, right? And you can supply it, then give it to 3, right? And you'll get the results, right? You get results, and well, and you compute them, right? There's also Mockingbird combinator, right? So this could be, of course, you apply a function to itself, right? There's omega combinator, true and false combinator, and y combinator, right? It's for recursion, basically, right? Hopefully this looks right. So if we define a function, right? So it allows a function to call itself without explicitly naming itself, basically, right? So it's central to functional programming for recursive functions, basically. So unless you do looping, I think without y combinator you wouldn't really have a Turing complete. I mean, it would not be equivalent, right? But it turns out it was, right? So, again, logic, theory of computation, functional programming in general. But again, I'm not going to make you do it in a lambda calculus, right? Because we have more practical things we want to do. So, again, what I want you to take away from this lecture in general is this idea of pure functions, right? I think most of you do that already, right? So something comes in, something comes out, right? So you don't use any global, you don't mutate state, right? So I would say in practical terms, this means that 90% of your functions, I don't know, 80%, 95% should be pure functions. If you do, you say, okay, if you want to go all 100% pure functions, that makes your life really hard. Then you end up in a Haskell world, right? And it's good for sort of like thinking, and maybe do some academics, but really not won't lead to any practical. It will make things actually doing things very hard, right? Because printing is a side effect, right? For example, right? You don't want side effects, right? There is no. You don't want to, you know, save a file. How do you save a file? How do you write a function to save a file? That's mutation. That's bad, right? So printing is bad, right? So again, most of course functional languages make decision, they let you have some side effects, right? So first, again, you want to have passive functions. It can be cool to pass a function to another function. For example, where would you see this? We'll see some examples in Python, right? For sorting, for example, right? Again, used quite a bit in JavaScript, of course, right? So this referential transparency, which we already touched on, is the fact that you can, if you have a set value, let's say, call function with, let's say, argument is 5, and you get 25 outside, you can replace that function call with 25, right? It doesn't change anything, right? There's no side effects, nothing is mutated, right? You can change it, right? You can sort of plug it in, basically, right? So, lazy evaluation, monads, well, we won't talk about monads today, no, won't scare you with monads, that's something from the type theory, right? Or not, we'll talk about that a little bit, maybe another time. But yeah, again, it's sort of like we declare, it's more, again, I wouldn't say it's maybe completely declarative, right? It's more, I would say, again, it's more declarative, right? Because we don't say exactly what should be done. That's what I'm saying, right? So it has higher level abstraction, right? There's data transformation, right? Basically, right? Again, so, but let's look at some examples, right? So this is a loop, right? Again, those who have used JavaScript, right? So we have some numbers, and we have a loop, right? Classical imperative style. So what would be the functional style? Again, JavaScript lets you do different ones, right? So you use something map and reduce. You might have heard these terms. Map and reduce in functional programming often used. So you have some numbers, right? We map numbers to their squares, and then we reduce them. We apply. So who knows what these arrow functions are? What are these arrows? Actually, I like kind of they are arrow functions, right? Do you know? You guys know? Anyone use JavaScript?
Yeah, well, it is like a return for the...
Yeah. So basically, it's basically like Lambda I just showed you. Like that Lambda from calculus, right? It's like anonymous function. It's a function without a name. It says you get x, outside comes x times 2, right? X times x, I mean, right? So we could have, at this stage, I could have given a function already declared somewhere, right? But here, since it's going to be thrown away, we make an anonymous function, or lambda function, right? So JavaScript added these arrow functions, I think, about 10 years ago, roughly, right? So again, it's heavily JavaScript. It's been often said that JavaScript looks like C, but it really is Lisp, really heavily inspired by functional programming. And reduce, we'll talk about reduce, but here the result is that actually it reduces two values, basically eventually to 1, right? Over some list. Okay, so let's again, not all of you, maybe not everyone knows JavaScript very well, right? So we look at, everybody knows Python by now reasonably well. So let's look at some pure functions in Python, right? And we'll get to some of the ideas here. But Python, how Python lets us write some functional code. All right, so deterministic, no side effects, right? Again, good for testing, good for debugging, good for readability. So let's look at some simple examples. We have Python, right? Do we have a function here? No, okay, let me see a function. Right, this is here. Okay, let's do it here, right? So, I know, pure function, fantastic, right? So, we can replace it, right? Again, so, we can replace the function call. Again, we have referential transparency because we can, right, exactly. So, hope you all agree with me right here, right? So, again, same thing. Right? Sum of list, right? Again, we can replace this with this, right? Of course, and here it's just, it's almost, this is almost, right? So it's not quite the same thing, but it's really, we're calling the built-in sum, right? So almost like an identity, but not quite, right? Right. More like a wrapper, right? Okay, right. So again, that's nothing special right now, right? So sum of list, right? Of course, we have some issues with types, right? We can sum some things, right? We do have issues, right? We do run into real life issues of types, type safety, right? Why does this work, right? So, should not right. So this actually works, right? So why does this work? Right, we get 9004, right? What's happening here? Maybe I'll make this bigger, right? Well, it's the way Python works, right? We have pi, we have 9000, and what's happening here? We have
1 and 0.
Yeah, we have 1 and 0, exactly, right? So Okay, so of course, if I try to do some RBS things, like something like that, right, it will not work, right? We cannot put string, we have a float and strings don't have concatenation, right? So, I already mentioned recursion transparency, right? We can replace this with 25, right? We saw this. Concatenating, we can replace concatenates function with just the string, right? Sum, we can replace with their values, right? So, again, it's hard to find like a good example of a non-referential function, but this, of course, as soon as you have globals, you have non-referential transparency because you depend on this global state, right? Which is, again, in general, globals are bad, right? Sometimes, right. So, one thing what's a core concept in Python, in a functional programming, is immutability, right? And well, Python is famously kind of loose, right? I mean, has a lot of mutable data structures like lists, dictionaries, right? They are mutable by definition, right? And even tuples, which you think are not mutable, actually they are sort of mutable, right, inside, right? So we do have some primitives, right? So we can get something, right? We can use immutable built-in types, number, string, tuples, right? Sort of, because again, when you use something like this, greeting replace world everyone, this is functional style, right? Because what's happening? Because the greeting is not modified. New greeting is created, right? So this fits within the functional programming paradigm, right? You can use some custom immutable types if you want, right? But again, Python is never going to be a pure functional language. But what I want to get to you is to get some ideas. The first class functions, right? Some ideas. So, right, we can have function like say hello is greet, right? We can rename, right? Again, Python lets you have functions as variables, right? So, right, let's look at this idea, right? This idea of this particular function. Let me see if I have this idea. Do I have it here? Let me see here. Oh, this is big, lots of examples. Right, let's look at the, right here. Right, yeah, closure, this is good, but let's look at the, creating apply function that will take a function and parameter. Yeah, so, right? Well, this is that would be really nice, but that's going too far. That's nice, right? To give you everything, right? But for now, I will. This would be a full example, right? Full example. But let's stick with something simpler. Let's stick with single variable. Yeah. So this means we have an apply function. And this means it will take the function and it will apply it'll use the argument or and return the result. So let's look at usage, right? Let's define. We have square already, by the way, right? We can define cube, right? Define cube x, right? And we can use cube. We can use print apply cube 3, right? So again, you think it's kind of like a wrapper, right? But turns out we can basically use this to, right, 16 and 27, right? So this idea that we can pass a function, right? So if we take this this effect maybe a little bit further, right? We can return functions. We can make a function that returns a function, right? So kind of interesting idea, right? So idea of a closure, right? So inner function, right? When we call add 5, we created a function that takes 5, right? And it will always, I called it add 5 function, right? And the 5 is sort of closed on, right? The value 5 right here, right? Because notice inner function only takes single parameter y, right? So 5 is sort of closed on. It remembers this, right? I can add 5, right? I can add print 5, add 10, right? So it will be 15, right? So 5 is sort of saved in because it doesn't, again, it's one of those tricks in functional programming, right? Closures, you might have heard of these things, right? It's a way of basically binding or saving a value, right, when we close over some inner function. All right, so another function, right, at -5, right, we can pass in and we get 5,000. Right, that also works. Okay, add subtract, right, So op name, right? We can store them in a list. So we can do things like this, right? For open operations, op name, right? So we can call add, subtract, min, max. We store functions in the list, right? We can do something silly like this, by the way. Add, subtract, min, max, right? We pass in a list, right? On this actually works, kind of funny, right? So look at this here. Operations 0 works. We called add with 5 and 3 arguments as parameters, right? Because so this is why. So add which was first item in our list, right? Which was function as first item in our list. And so you can do silly things like this. This actually works, right? Op name, undo. So remember, you can get the name of the function in Python, add, subtract, min, max, right? And it works, right? So things like that. So I mentioned closures already. Recursion, right? We already know about recursion, right? Fibonacci, right? And of course, you know the problem with recursion, right? Stack overflow, right? So there's some tricks actually that are used in functional programming, such as tail recursion, right? The way to optimize for this, right? Which basically means that it reduces to a loop, right? So tree reversal, of course, tail call optimization, right? Again, we heard about Fibonacci problems. We saw this in our algorithms course, right? So lazy evaluation, right? So things like lazy evaluation, right? So it are tools, lazy evaluation, but I want to show to end this Pythonic part of the lecture. I don't want to go about monads, strong typing. You can read about this more, but functional composition. Okay, so we can compose, right? Yeah. So things like this, right? We can use a compose make a function which returns anonymous function, of course, right? Which takes two functions, right, out of x, basically, right? So look at this example, right? So we can compose a function from two functions, basically, right? Increment after square, right? Kind of cool thing, right? So you pass in, so this compose function takes two functions and creates a meta, like a combined function out of them, basically, right? So, and of course, fg, right? Sometimes it makes difference how you call two functions, right? The order matters sometimes, right? Sometimes it doesn't matter for single value. For single value, let's see. If you have single value, it should matter. Yeah, it could matter, right? But here it doesn't matter, right? Well, it does matter here, you see? In this particular case, it does matter, right? Because whether you square after increment, right, is the two different things, right? You create two different new functions, right? Square after increment 4, right, it'll get you 25. But if you square first, then add 1, of course, you'll get 17, right? So you can do compose. Scary stuff, you can compose multiple functions, right? So Scala, you guys don't haven't taken Scala, so I will skip over that part. I want to get to the filtering part. Compose is good. Filter, map, and reduce, right? So Scala versions, right? And where's my map and filter? Oh yeah. The closure, but where's my map and filter? I thought I saw it. Map, filter. Oh, there we go. All right. Yeah, it's here, but it's in actually, yeah, map, filter, and reduce, and sort also, of course. Okay, let's take a look at some examples. Yeah, we can do apply. We saw that. Let's look at them. So let's look at code. Let's look at filter. Filter function in Python. Yeah. So filter. Who has used filter in Python? I think I may have showed you. No? Anyone? No?
In Python?
Yeah.
I think I have, but
Don't remember.
particularly remember
Yeah.
the use case
But
for it.
yeah, the thing is, okay, here's the thing. Some people, those who are really heavy in functional programming, they also like Python, they use filter. The thing is, for many things that filter does, list comprehension will do is even shorter syntax, right? So we'll show you. So, so
Does it work the same as in JavaScript?
yeah, yeah. Yeah, same thing. Yeah, basically the same thing. And again, it comes from these functional languages, right? So again, so let's see. Let's have a list of numbers. Yeah, all even numbers, right? So numbers, right, equals what? List range, right? 10, right? You know the numbers. Print OG numbers, right? These are OG numbers, right? And we will create a filter function for this. Is even, right? This is basically checks whether something is even, right? Right? On even numbers, list filter is even numbers, right? And we have print even numbers, right? So that's how it works, right? You pass in two parameters. So filter, it's a built-in function, right, actually from class, right? So you pass in a is even and numbers. And notice something else interesting as far as practical consequence is it's not actually, it doesn't give you a list actually. It actually gives you an iterator, right? Why does it do that? Why does it give you does not give you a list? Does anyone know? Any ideas? It's why doesn't give you a list immediately? Why do you have to call list for sure, right? So it gives you something at like a half ready, half baked basically.
To make it more efficient.
Yeah, of course, the answer is efficiency. So the idea is that you can do multiple, if you start chaining these operations, right? You don't want to keep making multiple lists, multiple data structures, in the middle of a computation, right? So this leads to very efficient code, actually, right? But yeah, so you can see this, compare it, right? So again, we could have done this with list comprehension, also even numbers, right? This also would work, right? Same thing. Again, so in my personal, again, as far as Python goes, I don't use filter very much because list comprehension usually is, I think to me, is a little bit readable. But again, of course, I use filter quite a bit in JavaScript or Scala, right, or other, languages which have this support. So filter is very nice, right? Again, of course, we could have done this iteratively, right, with a loop, right? Of course, yeah, and of course, we could have done this with regular iteration, on yeah, and of course, as you can imagine, right? So, and again, print also. Oh, come on, even numbers. Okay, I don't want to type. Yeah, on again. So hopefully, even before I finish typing, they all should be same, right? Right? Results same. So Python gives you three approaches, right, to filtering. Again, I should mention this that again. So this part here, right? This filter is even if you think about it, right? We'll fill this. If you think about it, we do not need a filter function beforehand. We can use lambda functions. Yes, that's where lambda comes from. So again, lambda iterative even numbers. So this is how you do it without. So here, right. Basically, this is how Python lets you do. So this is a way of defining function. Again, the scary word lambda really means it's an anonymous function. It's a function without a name, right? It just so if you compare it to our original, well here, right, or where's my Stanford encyclopedia, right? Where's my Stanford? Yeah, you can see it here, right? So same thing, right? Because notice there's no name. This here, it's using x as a variable, but the function itself is not assigned to anything. It's an anonymous function, really. So you can see it here for filtering, right? So for filtering, Oh, it's 11:57. Let's take a break till 12:10, and let's look at afterwards. We will look at map and reduce approach. Python.